Okie doke, it's time for neoclassical growth models, which means in this case the Solow model and then the Ramsey model. So, what does the production function look like in a neoclassical growth model? It looks like this. Refilled environmental friendly pen. Y equals F of AL, oh, it's kind of back to front. Here, I'm going to do it this way. ALL AKK. Okay, so Y is some function of labour and labour productivity and capital productivity. And the first derivatives, F prime L and F prime K, are greater than 0. Or greater than or equal to. And the second derivatives are less than or equal to 0. Yep, so more labour and more capital will give more production, or at least not less, but then there's decreasing returns. Yeah, if you keep piling on more and more labour, it levels off. Slide 8, the technology, it's non-rival, non-excludable and exogenous. Okay, so these change over time potentially, but exogenously they're just given. Everybody's got access to them, they're not excludable, and they're never used up. Yeah, they're not rival. If I use your technology, you can use it at the same time. It's not like pizza. Capital. How does capital develop? Slide 9. Typically, we model capital in a very specific way. Kt plus 1 is 1 minus delta Kt plus some savings rate times y, where y is this. Okay. And the special thing about the Solow model is that this savings rate is exogenously given. Okay. So more generally, like in Ramsey, the savings rate would be a function of the state of the system, the amount of capital you already got, or other things potentially. But here in Solow, we just say this is constant. So it's like 0.2 or something. 20% of what we produce, we keep back to produce more later. And what's this delta? I'm sure you'll know this, that's depreciation. Yeah. So, slide 10, and this is where I get you to start thinking. I'm not going to give you the answers here because we're going to do it on Zoom. Consider figure 1. What are the values of K, L, Y, and S? And what's the value of delta? Well, the only way you can know what the value of delta is if I tell you that the economy is in a long run steady state. Okay. If we assume the economy is in a long run steady state, you can also work out delta. Okay. I'm not going to say any more. I want you all to think about this and work it out for the Zoom session. And it's in the study questions, if you look at the study questions later. So you don't need to keep track of this. It's in the study questions sheet. Okay. So, do I need to say any more? No, you'll get it. Yeah. Just take the diagram literally. That's my only hint. Okay, take the diagram literally. I want numbers for K, L, Y, S, and delta. And units. Numbers and units. Okay, so another thing we do in the Solow model, which is different from the neoclassical model, is a more general model. The Solow model is an example of a neoclassical model. It's very specified, and typically in the Solow model we assume, well, we always assume that S is a constant, and we generally specify the production function like this. Oh, and we drop the AK implicitly, so we make that implicit, and we say K to the alpha. For the sake of, yeah, okay. For the sake of the units, keeping track of units, you might want to think of an AK there, AKK to the alpha. Otherwise the units don't make sense. Okay, but it's implicit. The way we write the equation normally, it's implicit, and most economists wouldn't think about it. Because I'm trained as a natural scientist, I think about units. A lot of economists, they're like, what, units? We don't need units. Okay. So this has some kind of interesting properties. Okay. One property of this is that the elasticity of substitution between the inputs is equal to 1. Now, would I normally go through this or not? Trying to think, would I guess it's a good idea to go through it. Just give me a sec. I'm going to pause so I can think through how to go through it nicely. Okay, so what's an elasticity? If we call it eta, what's an elasticity in economics? It's a sensitivity, and it's almost always a sensitivity of a quantity to a price, isn't it? High elasticity, the quantity changes a lot when the price changes. So it's the sensitivity of a quantity to a price. More specifically, it's the percentage change of a quantity given a percentage change in a price. Price up 10%, quantity down 10%, that's unit elasticity, isn't it? So what's an elasticity of substitution? So that is percentage change in relative quantity given percentage change in relative price, which we can call WL over WK. Okay? So that would be an elasticity of substitution, yeah. So if the price of labor goes up compared to the price of capital, what happens to the quantity of labor? And typically, we define elasticities so that the number we end up with is positive. So we put a minus sign here, yeah, because when WL over WK goes up, L over K is going to go down, yeah. Okay, so how would we work that out? Well, we would work out the prices, wouldn't we? And we need perfect competition. We need to assume perfect competition, yeah, for this method to make any sense. But assuming perfect competition, we can say that pi of some producer of this, that we can normalize the price of this to 1, and we can say pi is y, which is just this, minus WLL minus WKK. Yep. This would be the profits of somebody making this stuff. How much they can make minus what they have to pay for their inputs. Okay. I'm being super careless with notation here, but hopefully you get the idea, yeah. So then we want to say something about what these actually are, right? And to do that we take first order conditions. So if we take the first order condition in L, labor, we get dy dl, and then we're looking, this is y, yeah? So it's 1 minus alpha. Now, I'm going to teach you here to differentiate like an economist. What's that? We say 1 minus alpha. Normally you would say 1 minus alpha times AL to the 1 minus alpha, L to the 1 minus alpha minus 1, wouldn't you? Times K to the alpha. But I'm going to teach you to think differently. I'm going to think it's 1 minus alpha times y. Okay, but then we're dropping the power of L by 1. So it's 1 minus alpha times y divided by L. Okay. Some of you might be able to just see that this is correct. For others, you might need to work this out in the way you're used to and compare it to this and see that it's the same. I want you all to be able to do this. No trouble at all. Okay, it's really important for the course. So if you can't just see that, practice it, okay, until you've got the hang of it. I call it differentiating like an economist. You save so much time and trouble, and the risk of errors goes down massively. So that's dy by dl, and then we have minus wl equals 0. So the condition tells us, that 1 minus alpha y equals over L is WL. So we've got that 1 minus alpha equals WLL. And by symmetry, the condition in K gives us that alpha y equals WKK. So then we've got that if we divide one by the other, we get that WLL over WKK is 1 minus alpha over alpha, or that so yeah, where to start? This is super interesting, because this is what firms spend on labour, and this is what firms spend on capital, and this is saying it's always the same. If alpha is 0.3, for instance, this is saying that firms spend 70% of their revenue on labour and 30% on capital, and it stays the same. And interestingly, this is what we see in real economies, that it tends to, those proportions tend to stay the same, which is one of the reasons why we like using the Cobb-Douglas, because it fits the broad brush, long-run data. Okay, and if we put this, rearrange this, we can say that L over K is equal to 1 minus alpha over alpha, WL over WK to the minus 1. So then we can say that dL over K by dWL over WK is equal to minus 1 times L over K divided by WL over WK minus L over K over WL over WK. And given this definition, that is equal to dL over K by dWL over WK times WL over WK over L over K equals 1 minus that. The elasticity of substitution is 1. Okay, I hope you can see that. If we bring these over and the minus sign, you end up with 1. And this is how we define elasticities, isn't it? So the elasticity of substitution is 1. The factor shares of the inputs are constant. That's this. So if the price of labour goes up, you use less labour and the share of your costs going to labour stay the same, for instance. Super important. Okay, slide 13. Solve the model, given that alpha is a third and delta is 0.1. Characterize the long-run steady state. I want you all to do that, or try that, before the session, the session where we go through this. Okay, which is, well, as I'm speaking on Monday the 9th, it's in a week and a bit, isn't it? Discuss the effects of different savings rates across countries. Okay. So, what's this question? I'm going to pause the video and clean up here. Okay, effects of different savings rates. So we've got two different countries. One has S is 0.1 and another one has S is 0.3. What happens in the long run in those different countries? So you think this one is saving a lot more, so it should build up a bigger capital stock and get richer. But how much difference will it make when we have this production function and alpha is 0.3? Think about that. Okay, what if there's a global capital market? What difference would that make? If one country is saving less than another, what difference will that make? If there's so this first model was autarky, there's no trade. Okay, but if there's global capital market, then if there's loads of capital, or if capital is cheap in one country and expensive in the other, maybe those people saving a lot here will send their investments here where there are higher returns, perhaps. Perhaps. We'll talk about that as well on Zoom. Okay, I'm now going to work through the Solow model when AL grows. What happens to big Y and little y, y over L. Okay, and before I do that, I'm going to pause the video, clean up the board, and collect my thoughts. Okay, so what happens in the Solow model when AL is growing exogenously? Okay, so what have we got? We've got Y is ALL to the 1 minus alpha, K to the alpha. We've got AL dot over AL is G, or GAL, I'm just going to call it G on the board here. So this is exogenous growth at a constant rate. Yeah, I hope you all know growth rates. We've got L dot over L is N, another constant rate. And we've got K dot is SY minus delta K. So I've gone into continuous time here, right? Because it's more convenient for this kind of stuff. So instead of KT plus 1 is KT minus delta KT plus SYT. I've got K dot, which is KT plus, it's like, K dot is like KT plus 1 minus KT, isn't it? So if you think of this as KT plus 1 minus KT, then everything else is the same. K dot is the extra capital, yeah, over time. Okay, so this is the equivalent in continuous time as the continuous time one, the discrete time one we had before. Now, what is going to happen over time? We start with some capital stock, 100 hammers, or whatever. What's going to happen to the number of hammers? Well, if SY is more than delta K, the number of hammers will go up, won't it? And then production will go up. If SY is less than delta K, the number of hammers will go down, and so on. And you've seen this before, yeah, that we end up with a steady state. You've seen the pictures. This stuff, yeah, we're going to end up here. I'm not going to take you through that, and I'm not going to, you could set up a model in MATLAB and show what happens over time. I'm not going to do that. I'm going to assume we're in the steady state. So we're in the steady state, or we're in balanced growth. So let's just assume we're on a balanced growth path. On a balanced growth path, state variables must be growing at constant rates, which means that k dot over k is constant. Okay, this is super important. Okay, I'm going to say this like a million times during the course. But on balanced growth, state variables grow at constant rates, so k dot over k, which is the growth rate, is constant. If k dot over k is constant, then if we divide through this by k, we get k dot over k is s times y over k minus delta. Delta is a constant, so then y over k must be constant. So if we're on balanced growth, k dot over k is constant, which means that y over k must be constant. Okay. So if y over k is constant, what does that tell us? Well, this equation says, well, y over k is actually equal to al all to the 1 minus alpha times k to the alpha over k, which is k to the alpha minus 1, isn't it? So we can write y over k is al over k all to the 1 minus alpha. Okay. So y over k is constant. That means that this is constant, which means that ALL is growing at the same rate as k. The growth rate of the product of two things is the sum of their growth rates. Okay. So if AL is growing by 1% a year and L is growing by 1% a year, then ALL will grow at 2% a year. That's not quite exact, but at the limit, when we're differentiating, making very small changes, then that holds exactly here. So the growth rate of ALL is the growth rate of AL plus the growth rate of L, and that's equal to the growth rate of K. So that tells us what's going on in balanced growth. So N and G are given exogenously, so this is telling us that ALL, that's G, L dot over L is N, K dot over K is G plus N. But we also know that Y over K is constant, so that means Y dot over Y is equal to K dot over K. Okay. So production and capital grow at equal rates, and that rate is the sum of the growth rate of technology and the growth rate of population. What is the growth rate of Y? Little y, which is Y over L. Well, that's Y times L to the minus 1, isn't it? So what's dy dt? Let me see. This video is going on a long time, isn't it? I'm rushing a bit now because I feel like the video has been going on too long. I'm going to finish this off, and then I'm going to stop the video and go and help my daughter make supper. Right, so dy dt, what is that? How much does y change over time? It depends on how much big Y changes over time. Times L to the minus 1 plus let me start again. Sorry, that wasn't very clear. The little y by dt is the little y by the big Y by dt, plus the little y by the L by dt. What's this? How much does little y change over time? It depends how much does little y change when big Y changes, times how much big Y changes over time, plus how much does little y change when L changes, times how much L changes over time. The sum of those two effects gives us the total. So what's the little y, the big Y? That's L to the minus 1. What's the big Y by dt? We just call that y dot. So it's y dot over L, plus the little y dl, that's minus little y over L. Doing it as economists, minus little y over L. The L dt is L dot. So that's, and the y by dt we call y dot. So I'm going up here, we have y dot is big Y dot over L plus little y L dot over L. Is this right? No, this isn't right. Oh, wait, okay. I didn't differentiate like an economist. Terrible. Send me home. Right. The y by dt. The little y by the big Y. What's that? It's I thought of it as L to the minus 1, but we can also think of it as little y over big Y, can't we? Times y dot. So, little y over big Y. The other expression was correct as well, by the way. You would just needed an extra step. It's just nicer to go straight to this. So then y dot is little y dot over y, little y's and big y's. Let's just do this. Little y dot over little y is equal to big Y dot over big Y minus big L dot over big L. So the growth rate in production per person is the growth rate in overall production minus the growth rate in population. So population growth dilutes, obviously, overall growth, and we end up with little y dot over little y is just g. Okay, and that is the end of that solo video, and then we're going to round off with, yeah, a little bit more on solo, but this video has gone on too long.